Thank you very much. I hope the screen is mine indeed and that you see what I'm showing you, which is also my justification, like Ivan, why I am in this session. Well, I was PhD student of Alexei and Guillaume to some extent, because I was actually in Guillaume's office for all this time. I left in 2005, I believe at the same time as Ivan as well, and along with Alexei. And of course, I will not speak about the work I did as a PhD student, which, by the way, was the most humble contribution that was ever made by someone in this Polaritonic group, because it was a long time ago, but still I have to justify. So I will speak about this 11th chapter of the book. I don't know if you see me on the camera. The textbook Microcavities that was written along with Jeremy Bomberg, Guillaume, and of course Alexei as the first author. And this book we started to write in Clermont. So now I think I've justified that even though I will have no co-authors that did the work that I will present today, I've got a foot in this Polaritonics in Clermont-Ferrand, because that's this 11th chapter, which is indeed on quantum polaritonics. And of course, there is an historical element to this presentation, so I should say things about Alexei, but there is not enough time. And also, I think it's not appropriate for me to speak to the computer when we speak about Alexei. It's the opposite, actually. So it's very sad, it's very unfortunate that we don't have the chance to be in Clermont-Ferrand. At least I was born there myself, so I still could get some strong interaction with the city. But for everybody who would have come and never had the chance to be in Clermont-Ferrand, this is very unfortunate. You should go at some point, because it's not the most famous city in France, but that's one of the most interesting, definitely, with this black architecture, the lava stones, the volcanoes, everything, the Romanic art. So it's very sad, this COVID situation, and it's very unfortunate. Also, it's unfortunate that it was something that affected a lot. The last time I gave an actual talk, a real talk in the real world, which was for this celebration of Alexei's 50th birthday. It was at the beginning of all these things, not only in time in March, but also in the place where it started in Europe, in Italy. So certainly we have a role for the dissemination of this pandemic in the rest of the world. But anyway, so I was speaking of Polariton blockade at this occasion in Marino, and I'll speak about this as well during this talk. That will be part of my presentation on quantum polaritonics. And this work has been done with these people. So nobody from Clermont, they are all Spanish, from the University of Wolverhampton, myself from the Russian Quantum Center as well. That's for the theory part. And for the experimental part, this is this Uber group from Daniele Sanvito with Dario, Milena, Lorenzo, Vincenzo, and Daniel. That's the main people, I believe, from the experimental part. So starting with the Polariton blockade, it's been discussed already, so I will not go into the detail. You are all familiar with the shape of anti-bunching and bunching from this very important seminal paper by Verger. And already in microcavities, if you go to page 488, there we pointed out that if you don't stop plotting what happens with the two-photon correlation of the Polariton emission, if you don't stop there, but you carry on, you see that there are more things behind this. This is this part. The Verger panel is this little part that you see there, if you see my mouse. Behind that, it lurks a huge bunching peak and a huge anti-bunching peak. And this you can understand, in particular the anti-bunching, not discuss the bunching right now. It is this unconventional blockade or unconventional anti-bunching from Tim Liu and Savona, who rediscovered it in the context of Polariton physics, and I would explain subsequently by these people. So there is a lot of things that was hiding there. That's kind of interesting, and I'll discuss about that. But my first comment, first important thing, it's a point that we made in this paper with Lorenzo in 2014. If you look at the first equation of this paper, here we show the polariton as people like to imagine them. And we've seen actually this equation several times during this conference. So this is the superposition, quantum superposition of two Fock states, one photon and zero exciton, and vice versa. But actually, when you describe an experiment of this type, where you've got a coherent laser that drives coherently the microcavity, what you get is not this, it's something like that. So there is a one-to-one correspondence indeed, in the sense that the analytical expression for alpha and beta are exactly the same, they are the same quantities, but their interpretation is completely different, because here we've got quantum probability amplitudes, while here we've got a classical amplitude, like classical field of the electromagnetic field, for instance. And here there is no entanglement, this is a factor product. It's very easy to show the algebra that there is some connection between these two things. But this is purely classical physics that is cast in with terms of quantum mechanics, with notation of quantum mechanics, but this is otherwise completely classical, while here we've got an aspect of genuine or real actual quantum mechanics, in the sense that it's non-Gaussian. So that's why I would myself define quantum mechanics. It's something that is non-Gaussian. And I will not go into the detail of this very nice paper of Lorenzo, but just to belabor the point, I will show you in the phase space the quantum state. So this psi here for various types of motion that are familiar to everybody. So that's the Rabi oscillation. We've got the cavity field in red and the exciton field in blue, and that corresponds to the Rabi oscillation. For some representation, which is not precisely Wigner, it's the Ussimi representation, but it doesn't matter, you get the idea. So it becomes important if we compare with the next animation, where I show you the lower polariton. So we've got out of phase oscillation going in this direction, and the upper polariton is like this, they're in phase and they rotate, this time with the rotating frame, so with this splitting in energy. So that's the good way to think about Gaussian state of polariton when you describe, when you excite your laser, when you drive it, your microcavity with a laser. Even if the interactions are not completely negligible, that becomes exactly the interactions are zero. So in 2015, we propose not to do this scheme of exciting the cavity with the laser, because that would bring us to this Gaussian polaritonic physics, which is not strongly quantum, but instead excite it with the output of quantum light. And the output of quantum light, it could be, for instance, the emission of a two-level system. Here now we've got non-Gaussian Fock state. And what happens if we drive our microcavity with this thing? So there, a first experiment has been made, not exactly of this configuration, but of something a bit similar by the group of San Vito in collaboration with other people that are experts in using quantum excitation. Namely, we used, they used an entangled photon source. So two photons, one that will excite the cavity and the other that will be left to carry along. So this nice animation that shows you that one photon transforms into the polariton, and you recognize the Rabi floating between exciton and photon, and it keeps this entanglement with the other photon. And when the polariton re-emits or reconverts into a photon, then we can look at the correlation of this thing and see if if we maintain the quantum correlation outside of this structure, when the polariton became a photon again outside of the thing and is measured in the laboratory. And indeed, it's been observed by measuring the Bell's inequality violation. This is this figure 4 there of this paper, that we have the perfect, very good, we maintain very well the entanglement of the polariton, and this time a non-Gaussian Fock state, one single polariton, so it's not a Korean state with two particles, it's one Fock polariton, non-Gaussian state, which not only is there, it quantizes the polariton field, but it's also non-locally correlated with a photon which is outside of the laboratory. And there were more aspects of this work. In the second line, we actually did the same experiment, but not with the cavity in the vacuum, this time with a Bose-Einstein condensate inside. And we've seen that depending on the size or the magnitude, the intensity of this condensate inside the cavity, this affected the concurrence, which is a measure of the entanglement between this photon or this polariton and the photon that goes straight through the detector. And this looks like a simple basic decoherence or dephasing of the effect, but not at all. It's something much more interesting. What happens is that every polariton that is inside the Fock polariton that we injected from our quantum source, it sees the condensate, and the condensate fluctuates. Condensate has this Poissonian fluctuation, so the number of polariton we got for any single polariton state is not the same, and therefore the dephasing, so quite in the same way that we've seen from the Sheffield talk, except that we did it with quantum states, with Fock states, the dephasing is not the same. So when you look at the coherence at the end over this several repetition of the experiment, because of course you need to do this millions of times to acquire a signal, then you observe a reduction of the concurrence, but not in the trivial detrimental way that we are dephasing the effect, rather in the fact that we are measuring or sensing, seeing the fluctuation of the condensate without perturbing or without spoiling the entanglement. So that was one first experiment, 2018. More recently, Daniel, which is he looks like on Zoom, he did the other experiment that was the one that was proposed initially in 2015, was to send a single photon directly from the output of a two-level system. So that's the sketch of the experiment. He sends the photon one by one. These photons, they become polariton, and then they propagate a single polariton. And for us, I don't have time to put my discussion in perspective from the previous talk of Alexei regarding of what's interesting or not with quantum polaritonics. Everything is interesting, but for us, that's the ideal way, that's the ultimate definition of quantum polaritonics. Here you got a polariton Fock state that propagates, and we all like, of course, the propagation of polaritons. So then these things propagate for some time, it's re-emitted, and they image it on the strike camera, and that's what they see. If the single polariton, which here has been integrated over millions of iterations, of course, so that makes a finite signal at the end. It looks like it's a fluid that propagates, but it's not a fluid. It's one polariton that propagates, and if it propagates in free space, nothing happens. But if you send this onto a defect, what you see is this double slit experiment. You see these fringes. And this is really interesting because the double slit experiment has been described by many bodies, by Feynman, for instance, as the most perplexing experiment in physics. But here it's like an obvious extension because we see it in space-time entirely. We don't have to put a detector at the end to see the fringes. We see them in the entire plane of the experiment. And this can be simply explained, the pattern that we see, as the interference between the plane wave of the polariton before it interacts with the scattered spherical wave after it interacts with the defect. So it reproduces very well this linear experiment. No interactions there except the interactions of the single polariton with the defect. So that's very interesting because we can start to look at fundamental aspects of quantum mechanics, like the non-locality or this wave-particle duality. This is work in progress, so I will not detail it too much, but we are considering what it has to say, this experiment of this LAUSSY experiment on the propagation of single polariton, making the double slit experiment in terms of the wave particle duality. So here we've got a case, ignore these fringes there, that's where we have the potential. We've got a case, we've got a particle before, it's the wave packet that propagates, so we can follow it, that's what the particle is, something you can put your finger on and follow. We've got the part which is refracted, so it's also a particle after. And if we look at the exact same propagation, same experiment, everything is the same, but we put a detector that doesn't affect the dynamics. It's just observing this effect, and this detector has not the perfect time resolution. Then we see something like this. We see the fringes that are much more extended. So here we've got particle behavior, and here we've got wave behavior. And all this not because of the object itself, but because the detection that we make of the object. And that brings me to the second aspect of my talk, which is on the wave-particle duality, in something a bit related, which is resonance fluorescence. So I'll explain to you at the end why I need to make this detour on resonance fluorescence, but the idea is very simple. We've got the two-level system. We drive it strongly with the laser. We drive it with the laser coherently, not strongly, actually. We drive it weakly. We are in the Heitler regime. And the emission of this, we can simulate it with this formalism we published some time ago, some Monte Carlo procedures that goes beyond the quantum Monte Carlo that you know. We can feed that to the Embry boundary setup and compute numerically from this simulation the anti-bunching, compare it with the theory, and we see the perfect anti-bunching, of course. If you look at the same time at the spectral shape of this thing, you see that it's very narrow. It's basically a delta peak, Dirac delta peak. That's the Rayleigh scattering. So here we've got wave-particle duality. We've got something that behaves like a particle because the photons tend to arrive one by one, but it's also a wave because it is very narrow. It's like a sine wave, very perfectly defined frequency. And so this has been reported by people a long time ago, already 10 years ago. And I want to look at the details of the experiment. I want to bring your attention to what happens at the foot of this Dirac delta function. Here we've got the incoherence fluorescent, the emission which is not scattered by the laser, but that is the one emitted by the two-level system. And therefore, the total emission of our system can be decomposed in this elastic scattering pink, which is the mean field of our two-level system annihilation operator sigma, and the luminescence itself sigma. And the relation between these two is that their sum provide the two-level system operator. Very nice. But now, when we've got, okay, very nice and very general. You can always take any operator and decompose it into its mean field, and the difference of the mean field with the operator, which we call the fluctuation, something that is very familiar in quantum field theory, for instance. But when you've got something which is the sum of two fields, a field which is the sum of two fields, it brings right away this concept of interferences, right? So the intensity should be the sum of the intensity of one field plus the intensity of the other field plus this interference term. But of course, by definition, the fluctuation have no mean field. That's obvious from this point. Therefore, the sum of the intensities is this one. And of course, people know that, it's well known, it's published, everybody describes intensity in this term. But for the two-photon interference or multi-photon interference, the same principle appear. And there, interestingly, people don't tend to think in this term. They don't look at the interference of the scattered peak from the driving laser and the fluorescence of the system. And that's what happens in the G2. It's the two-photon and multi-photon G3, G, and so on and so forth. They are all explained in terms of some interference between the scattered peak and the fluorescence. So the interference is a bit more complicated. It takes the form of the addition of these four terms, where one is basically the laser there. And I won't go into the details, but the main point is that this I node describes the Fock state aspect, the non-Gaussian aspect of the field. And this I2 describes something else, which is the Gaussian aspect, the squeezing, to be more accurate. And when you look at the anti-bunching of this system, you get the anti-bunching as a result of this configuration, where you mix a coherent state with a squeeze state. So squeeze state, you all know what it is. You can get at the output, so it will be a density matrix if you discard one branch, but you will get a displaced squeeze thermal state. And this is anti-bunch, right? And therefore, the anti-bunching, as the mixture of a current state and squeeze state, is perfectly transparent. What we do is that we look at the P of n, the distribution of photon for our Poissonian distribution. We can cancel the two photon component by adding to something which oscillates for the probability to get 1, 2, and 3. If it's not the same, if one is seesaw, which is the case of the squeeze state, and the other is smooth, which is the case of the current state, then it's easy to find a condition that will cancel the two photon component. And therefore, that's the quantum state of the emission of resonance fluorescence when we drive it weakly. It's a displaced squeeze thermal state. And that's where the anti-bunching comes from. We demonstrated it, or we showed it, we confirmed it experimentally in this paper that has been published recently. Here I show you the G2, which is exactly 0 all the time, perfect anti-bunching from the output of resonance fluorescence in different driving regime. Omega is the intensity at which we drive the system. So we discussed this case at low driving where the anti-bunching is due to squeezing because of this I2. And there is no quantum or Fock or non-Gaussian character of the anti-bunching in this regime. And you might say, of course, that it doesn't look like there is squeezing at all here, but this is because the squeezing is very small. The eccentricity is very small. And it's very small, but that's what produced this perfect anti-bunching, right? And this is to be put in opposition with the anti-bunching we get at high pumping, where there we have the anti-bunching that people have in mind when they speak of the emission of the two-level system. It's because you put it in the excited state. It cannot excite with two excitation because it's truncated. Therefore, it emits photon one by one. That's true, but only in the high driving regime. In the low driving regime, the system doesn't even know he has a thing that doesn't have a second excited state because the excitation is so small. So the anti-bunching is of a different origin. And why? So this has been published in this paper, as I said, and also I must mention another paper by the Manchester-Sheffield collaboration where using different interpretation, they arrive to the same results. So why I'm saying all this? Because first, there is something interesting we can do. As I said, the anti-bunching, it's spoiled by the observer, right? The wave particle duality, there's no problem until you start to look at it. That's opening the Schrödinger scat box. So if I put an observer, or if I filter the thing, which is the same, what will happen is that instead of seeing the perfect Dirac delta function, I will see this broad peak, right? Because I'm using here a detector that filter over all the frequencies. I'm detecting all the frequencies. Therefore, I don't have good frequency resolution, but so I don't see the good spectral shape. I see the perfect anti-bunching. If I improve my frequency resolution, you see that I improve my spectrum, but I spoil my anti-bunching, okay? Till this point where now I've got the anti-bunching of the emission, the relative lifetime, but the anti-bunching is quite weak. And if I go sub-natural line width, now I've got a better line shape. I'm starting to see my relay peak, but I lost the anti-bunching. If I make it very, very narrow, focusing exclusively on this scattered photon, I can even thermalize my photons. And of course, thermal state is like the opposite of a Fock state, right? It's chaotic. Okay, so there is a nice thing that we can do here is to compensate, to correct for this, because as I said, the anti-bunching is lost by the effect of, I will skip that. That's just to say that when people tell you that you can get optimum line width and optimum anti-bunching, this is true, but not simultaneously, not at the same time. You can get the upper line or you can get the lower line. But now, okay, so if we come back to this interpretation that the filtering, what it does is to perturb this perfect interference, this two photon interference, by removing more of the incurrent fluorescence than the scattered peak. Yeah, actually, it's easy to compensate. It's easy to compensate because if we have too much of the current state, we can, by putting another current state in destructive interference, remove this excess of current state and restore this perfect two photon interference. So we proposed in this paper here with Camilo to do this, to mix on top of the emission of the two-level system a part of the driving laser, which is properly attenuated in phase and in amplitude, so that in the mixing, then we restore this two photon interference. And indeed, we show that we've got both this time simultaneously the subnatural line width emission, so something that behaves like a wave, and the anti-bunching, which remains perfect. On top of that, even with a better coherence time. Okay, so that brings me back to our Polariton bouquet story, because actually,
3 minutes.
3 minutes? I thought I had only 2, so it's welcome information. This doesn't apply only to the two-level system. It applies to all systems that you excite coherently, or every system that can accommodate a current state of some sort. Like, for instance, every system which have a cavity. like our Polaritons. Our Polaritons are something which has a non-linearity inside the cavity. So all this physics that I explained for the two-level system applies to a wide family of things. And in this review that I invite you to consult if you're interested, we describe the two-level system, the resonance fluorescence, the anharmonic oscillator, the James-Cummings physics, the Polariton, everything is in there. So there's a lot of physics that look disparate and that people have attacked in different directions, which actually all gets down to this interferences of fields, of the current field and a squeeze state. So let's look at the James-Cummings case first. This is the detuning of the cavity. I've got my two-level system at 0, and this is where I would drive the system with the laser. So you recognize the lower polariton, you recognize the upper polariton, and we can now explain all this photon correlation. There's 2 photon correlation there. In terms of, if I separate the numerically exact result with the analytical theory, we can explain it in terms of different types of what we call conventional with C and unconventional in U, to connect with the literature, yeah, with this TMU and Carusoto, Chuti, Imamoglu terminology of conventional and conventional blockade. But for us, it's not blockade, it's photon statistics, because there is no blockade, it's interferences, right? So I don't go too much into the detail, just keep in mind the structure, because that brings us back, as promised, to our Polaritons. One last thing, actually, you remember that the first slide I showed you that in the Verger paper, they didn't go far enough to see the unconventional. So interestingly, the same thing happened this time with the experiment from the Imamoglu paper. They cut short enough to see the unconventional blockade, which was there. They might not have seen it because it was off branch with little signal, but still, it's interesting that it's always outside of the figure. So the Polariton, if you compare this structure with our Polariton, the difference between James-Cummings and Polariton is that the nonlinearity is really weak. As a result, we've got differences. Like this line, for instance, it got bent like this, yeah, because the nonlinearity is really weak. So when people tell you that there is this anti-bunching peak, which is characteristic, it's not characteristic. It's because we are bringing together the anti-bunching and the bunching line. So the anti-bunching resonance plus the bunching resonance that are put together from the James-Cummings, they produce this thing of the Verger shape. But more interestingly, this unconventional line of James-Cummings now is transposed on the other side here, and it can cross with the conventional line. And this is really interesting because unconventional correlations are very strong, but their emission is very small because they are off branch. And here we've got the best of 2 worlds, because we can bring together, we can intersect the unconventional strong anti-bunching with a strong emission of being on the branch. Therefore, if you look at, this was the case for strong interactions of Polariton, if you look at the case of weak interactions that we have here samples, if we compare what happens there on this branch, on the lower Polariton, which is what people do, the Nature Material 2 papers on Polariton blockade, they look there with the very small anti-bunching. If you look at the same thing on the upper branch, you would see, thanks to the proximity of the unconventional blockade to the conventional anti-bunching, you would see a much stronger anti-bunching. So a trick is to use this. Okay, I'm running out of time, so I will just say that there are also tricks to bring this mixing, this intersection of the unconventional anti-bunching on the lower branch, but this is not published and I don't have time, so I will go directly to the conclusion, which I will not read. I will just pause, not for effect, but for the video to record it, and then you can pause and read them for yourself, and go to the references. So for everything that's before 2017, when we published this book, I refer you to chapter 11. For everything that we did ourselves post this date, I refer you to this, this list of work. But basically, this laser and photonics review, you'll find our scheme on the cover of homodining the output to maximize the photon correlation. There we have all the possible details, including Polariton. With this, I stop my talk and be happy if I left a bit of time for questions.
Thank you very much, Fabrice. Thank you very much for this very interesting talk and very interesting results. Indeed, we have a couple of minutes for questions. Questions, comments, please. Alexei?
Yes, again, a philosophical question. So as a Chinese scientist, I am very proud of boson sampling experiments by Xiaoyang Lu. But as a polaritonic scientist, I feel that Polaritons is an ideal system to demonstrate quantum supremacy through boson sampling. So what is your opinion on that? I know that you thought about it also.
On boson sampling, but doing what? I mean, boson sampling, it involves these highly correlated input photons, yeah, which again are highly non-Gaussian. So it's not quantum supremacy in the sense of Lagoudakis, where he's using this current state. So which
yes, but why would not you with Sunvito demonstrate boson sampling with Polaritons, just injecting single photons from different sources?
Well, it's very simple because the people who know how to do that very well, like this Shalino collaborator, they find it very hard to have n photons that can propagate in this setup of many interferometers. It's highly difficult technically, but I believe there's a lot of progress in this direction. Actually, we have ourselves a proposal to make something which is not exactly boson sampling, but it's linked to the complexity of emission. It removes all the interferometers. It consists in making n photon correlation from the output of resonance fluorescence with corrections for different intensity due to the spectral shape. So we've got some proposition, but this time they get rid completely of the polaritons. So I don't think for the polaritonic sessions in Clermont-Ferrand, I need to discuss them furthermore.
Okay, maybe some other questions or comments? Well, if it is not the case, let's thank the speaker once again.